with knowing the physical um, quantities that leads to systems of equations. Let's look at how these equations are being written. And I forgot to let you know that we are looking at linear systems only. So far it has been linear equations because we can easily solve linear equations. If it's nonlinear, it has to be converted to a linear case. So the structure of linear systems. How would it look like? I'll be using my slides to help you understand whatever I need to talk about. So it's always in a form as the representation in the slide. If I have it as some x1 prime and then some coefficients of some other variables. You know, prime means you're looking at the change of rate. So this is some plus j1 through to some plus jn. If I have it this way, I can rewrite this in a matrix form as having x1 prime, x2 prime through to, so I thought the prerequisite for this course is to know your matrices operations. So I can write this one as x1 prime, x2 prime through to some xn prime equated to, I can list out the coefficients from this and have the unknowns as x1s, x2s through to some xn plus the source term j1, j2 through to some jn's. What are the elements in this matrix? The first coefficient is a11. I'll have a12 through to some a1n. The same way for the second part, a21, a22 to this. This will now move me to some an1, an2 through to some ann. I hope you remember these matrix representations out of systems of equations. So I can denote this as a capital X prime is equal to some capital A. So this is X, this is A, this is the prime. Now this is some G. Let me just use capital G. Now look at this system very well. If my genes are zeros, it means I have homogeneous equation. If they are not equal to 0, it is a non-homogeneous equation as we've already established in the higher order. Now knowing this, let's see how you can, my next thing will be how to extract systems. So how do you move from a higher order to an nth order to an n systems of first order differential equations? So I've talked about the matrix vectorization as seen in the slides. I've explained that. Let's look at the next thing, how to reduce from the nth order to some n systems of equations. I'll take two examples, one on homogeneous and the other on non-homogeneous. Example 1. Assuming I have an equation as this, plus y is equal to 0, with some initial conditions giving us y of 3 equal to 0, y prime of 3 is equal to 1. This is the equation to solve. You realize that there's a linear equation. It is a higher order equation because the order is 2. It is also some constant coefficient, and it is homogeneous because the GT term is 0. Now what comes to mind if you see this? You can easily solve this using the roots solution. You can classify your roots as whether it is real and distinct, it is repeated, or it is complex. If you know your roots, you can describe your solution. That is one aspect we've already learned. Then the new thing is that we want to reduce this into some system. So the first thing I'll ask myself, what is the nth order here? It is 2. What is the nth order? To know the difference. So I want to know the highest order here. That is y prime prime as a subject. That will be equated to 5y prime minus y over 2. Okay. Now because the higher order is 2, how many systems do I expect? So I'll do number of systems of the first order differential equation. I expect 2 systems because the order is 2. So next thing, how do I write these systems out? I'll set some new variables. So the first variable, I will say let x1 be equal to y, and let x2 be equal to its derivative. These are 2 systems. The next is to differentiate these systems. So x1 prime, you realize that is the same as y prime. x2 prime will give you y prime prime from equation 1, equation 2. Now if I want to look at this to respect to the new variables here, you realize that this is the same as x2, and this is the same as, I have this as equation star. This is the same as equation star. So that is the same as 5y prime minus y over 2. But I want my terms as the new variables. Y prime is the same as x2. Y is the same as x1 over 2. Everything must be in terms of the new variables I have set. So you realize that the system now is some x1 prime is equal to x2. So I'll have this as equation 3 and then equation 4. From equation 3 and 4, I can rewrite it as x2 prime giving me 5x2 minus x1 all over 2. This is my 2 systems of first order differential equation. You know why it is first order? The highest order here is 1. So from second order, as this, we've reduced it to 2 first orders as a system. Now the question came with some initial conditions. The first condition was y at 3 equal to 0. This implies that if I want to use the new variables, y is the same as equation 1. From equation 1, y is equal to x1. So it means x1 at 3 equal to 0. The second condition was equal to 1. Now y prime is the same as what? x2 from equation 1 and 2. So it means x2 of 3 is equal to 1. Now this is the new conditions that need to be solved together with the new system. If I want to write the matrix out from this, you realize that I need some x prime is equal to some ax plus some g. My x primes becomes the 2 new ones. My a is the coefficient of x1, x2. Now for this question, g is 0. It was homogeneous. So let's set the a. From here, the coefficient of x2 is 1. The coefficient of x1 is 0. From the second system, if I split this one up as negative x1 over 2 plus 5x2 over 2, you can tell that the coefficient for x1 is negative half, and that of x2 is 5 on 2. And that is it for the first example on homogeneous. The second example, that will be on non-homogeneous. Let me change the marker. If I have the third order, so y prime 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 minus 2, let's take minus y minus t equal to 0, with conditions giving us y1 is equal to 1, y prime at 1 is equal to 2, y prime prime at 1 equal to 3. These are initial conditions. Quickly, you know that this is a linear equation. It is a higher order. It is constant coefficient, and it is non-homogeneous. How? I can rewrite the equation as this. This is a non-differential term. So because of this term, this is non-homogeneous. Quickly, I can solve this using either the method of undetermined coefficients or VOP, variation of parameters. You must get an answer. But if you want to look at alternative 2, it means we want to solve or break it down to systems of equations. So the first question, what is the highest order? It is 3. What is the nth order here? It means y prime prime, that's the third one, will be equal to t plus 2y prime plus y. How many systems do I expect? Number of systems do I expect to have? I expect to have 3 systems and then 3 initial conditions. IC means initial condition. Okay. And so I need to set new variables. So 3 new variables. I'll make it x1 to be the y. I'll take x2 to be the first derivative, and then x3 to be the second derivative. These are my 3 new variables. The next thing is to differentiate these variables. So let's see. x1 prime will give me y prime. x2 prime would give me y prime prime. x3 prime will give me the third derivative. Now I want to convert these ones into the new variables. You realize that y prime is the same as x2 from equation star. Y prime prime is the same as what? x3. What about the third order? The third order here, we can take it from the nth order here, which was giving us t plus 2y prime. Let me check it well. Plus y. But this is not correct. It has to be moved into the new variables I have set. So this is equivalent to writing t plus 2, y is x2, and y prime is x2, sorry, and then y is x1. So you check the new variables and then you do your substitutions. You do your substitutions after the differentiation. Now can we write the new systems of equation? It becomes x1 prime is equal to x2, x2 prime is equal to x3, x3 prime is equal to 2x2 plus x1 plus t. With the initial conditions given, y at 0 means I'm going to get x1 at 0 equal to, which conditions did I use? 1. Y prime at 0 means I'm going to get x2 at 0 equal to 2. X prime prime at 0. Prime prime is given as x3. These are the conditions that came with it. It is all from the new variables. Hence, I can write the matrix notation of this example as big X prime is equal to AX plus the G. My X prime is the 3 variables here and its derivatives. A I'll look at it later. My unknowns is x1, x2, x3, and then my g, it is 0. Wait, let's hold on to that. So let's compute the matrix A. The coefficient from the system that x1 is 0, 1, 0, because it's just that. If I take the next part, you realize all the terms is 0 except x3. If I come to x3 part, the coefficient for x1 is 1, x2 is 2, x3 is 0, but it has a term t. So it means 0, 0, and then t, because it was non-homogeneous. So this is how I would have written my matrix form for the same problem. It means if I solve this by the system and I still solve it by the MOU or VOP or the system approach, I must get the same answer. So this is how you convert from the nth order to the higher order, the systems of equations. If you have fourth order, it means you have 4 systems of first order differential equations. In the next video, I'm going to take how to solve systems of equation. All right.